Hi everyone, my name's Adam. Welcome back to part 7 of my video series on creating a flight controller using X-Plane and LabVIEW. In the last video we added an integral term to our controller, and in this video we're going to take a look at what that does to our system response and why. I've decided to try and break these videos up and make them a bit shorter, so this video will only look at the system response and we'll look at implementation issues in the following videos. Let's get going. Okay, let's have a look at what our integrator does to our system response. So first of all, here's the system flying in proportional only control. I've just adjusted this gain down a little bit, but otherwise it's the same. So we still have our steady state error of 2 degrees, like we'd expect. So let's put a square wave in and see what proportional control gives us. So we can see that the proportional control is giving us some overshoot when we're in negative pitch and is undershooting when we're in positive pitch, which is reasonably intuitive, but we've always got that steady state error. And we get a little bit of oscillation, but not too bad. And that's just a function of how much gain we've got. So let's now add in our integral term and see how that changes. So you can see as soon as I add that integral term, it's working to eliminate our steady state error, which is good, that's what we want. And now we've still got some overshoot in the negative direction, which we had before with proportional control. But what we now see that we didn't have before is we now have overshoot in the positive direction as well, whereas before we were undershooting and we had a steady state error that set us below our set point. Now I'll stop that the next time it happens and we'll have a look at why. Alright, so I've added this additional graph over here, and what this graph is showing us is in yellow we have our integral value as it's being calculated, and so it uses this left hand axis, and in green we have our error value, and so the green graph here is the difference between the red and the white curves over here, and it's using this right hand axis here, and so that's error in degrees. So I'll pause this when we've got some more data. Okay, so what's happening with the integral, and the reason that we get that overshoot generally is that if we look at integral, the integral will continue to grow whilst ever our error value has the same sign. So we will have a positive integral that will continue to grow while ever the error is positive, or if we were going the other way, we'll probably have a negative integral that will continue to grow while ever the error is negative. So what happens is we get this initial spike in error when we get our step change here, because the aircraft can't possibly follow a step change. It's got inertia, so it takes time to accelerate. And so we get a large error here, and then as we head up towards our set point, the error drops off rapidly. But it's still a positive error, and so our integral continues to grow through this whole period. And get a little bit of an oscillation here, and it's not until this point right here that the error actually drops to 0. So that's the point where we reach our set point, which is this point over here. And what happens at that point there, that's where the integral reaches its maximum. And now that the error has become negative and has gone down below our 0 line here, the integral will start to decrease again. But if you recall down here, our components and our gain, and you remember back to our block diagram, our integral term is the integral multiplied by some gain, in this case 0.001. And so what this means is that our integral term continues to grow right up until the point that the error becomes 0. So it's increasing its control deflection all the way up until we hit the set point. Now, depending on the system, that could actually mean that the system's continuing to accelerate right up until it hits the set point, or at a minimum where we're adding more and more control input. So that's the basic reason that we tend to overshoot with integrals. We won't always overshoot. If we have a very, very small integral gain and a system that's naturally damped, which pitch is to some degree, then we can avoid the overshoot. But at that point, the integral's also not being very useful to us. It's not doing much. So with any sort of useful integral gain, we're generally going to have this overshoot, and that's again because right up until the point where we hit the set point, at this point here, the integral gain is feeding in more and more control input, and then it's not until the error actually goes the other way to the other side of our set point that the integral starts to wind back and work towards whatever's going to be an equilibrium value. Another way we can visualize what this is doing maybe a bit better is, I'll just back this off a bit, and we'll try running the system just with integral control without any proportional control, and we'll see what happens there. And so you can see now we get quite a lot of overshoot, and because pitch is damped, it's going to oscillate around, it's going to decay, and it will get back to our set point if we left it for long enough. But we do get quite a bit of overshoot. So the reason we get less overshoot with proportional enabled is because as soon as we go past our set point, the proportional control will start acting to oppose the integral control, and they'll actually be working against one another for a period of time. And we can actually see that down here. At this point here, you can see proportional's actually gone negative, while the integral term is still positive. So the proportional would, if it was enabled, would be working against it. And so that's okay. So in pitch, we could have just an integral driven controller, and it would work. It wouldn't be great. We can reduce the amount of overshoot by reducing the gain, but that also makes the system slower to respond. However, if we look at an axis that's not naturally damped in the same way that pitch is, if we were to look at roll, for example, and we were to do the exact same thing, we can enable integral control there, and it may even do it without any intervention on my part. No, we might need some. Oh, there we go. So you can see, even without any input from me, just through natural disturbances, it's starting to oscillate, and that oscillation is going to grow in magnitude because there's not enough damping in the roll axis. So there was two things occurring there. One is that the roll axis is not naturally damped in the same way that the pitch axis is. There is resistance to roll, but not nearly as much as there is in pitch. And the other thing is that in the roll axis, increasing amounts of aileron will produce an acceleration in the rate of roll, and our integral control is adding more and more control input. So every time it returns towards that set point, it's actually accelerating the whole way up to the set point, and then it overshoots, and then it accelerates back, and so on. So we wouldn't typically use an I term on its own. We would only normally use it in conjunction with a proportional term, but hopefully maybe that makes it a little bit clearer what the I term does on its own. So one of the reasons that we have as much overshoot as we do, say in this pitch axis, if I start my square wave again, is that there's this initial period where we have a step change in response, and the air can't follow that, So there's this period of time, and we can see it over on this graph too, where we have this quite large spike in the error value for a period of time. And that means we build up quite a large integral value quite rapidly at the start of the step change, and the overshoot is basically a function of that initial integral that we build up in that little triangular area. There's a few ways that we can work around that. So the main reason that we're including this integral term is to eliminate steady state error. So one of the ways that we can minimize that overshoot is to disable the integral term until we're close to our steady state. And that might be close in terms of degrees. We might say, only enable the integral term when we're within 3 of our set point. And that might work fine if you know that your system can always get to within 3 degrees using only proportional control. That might work. The other way could be that we could look at the rate of change or this variable and say, once the rate of change is below a certain amount, then we've reached steady state and it's time to enable the integrator to remove that steady state error. Another thing that we can do is we can limit the rate at which our inputs to the system change. So the reason we're accumulating this large overshoot here is because we've got this step input. So maybe we don't want step inputs. If I keep these same parameters but change to a triangle wave, what we should see is that we don't get nearly as much overshoot, because the rate of change of our set point is more controlled. And you can see there it changes at the peak of the triangle wave, and we've got quite a small amount of overshoot, and it comes back to our set point value and tracks that fairly well. And if we were to use a sine wave, it doesn't have any sudden transitions at all, and so the aircraft should be able to follow that quite well as well. And so that could be as simple as putting a rate limiter onto the set point for the controller. I hope you enjoyed this video. In the next video, we'll look at how to implement some of the strategies to limit overshoot and see how they perform. If you have any questions, comments or feedback, please post in the comment section below. If you found this video interesting or informative and would like to see more videos like it in future, please like and subscribe.